Welcome to the session number 2 from the playlist of electromagnetic waves. The topic is the conduction current and the displacement current, and based on this topic I have written here 4 important points which will help us to understand the conduction current and displacement current in brief. So as we all know that conduction current is due to the flow of electrons in an electrical circuit, whereas a displacement current comes into play in a region or space when electrical field or the electric flux changes with time. So, in order to understand this topic, that is conduction current and displacement current, I have drawn here one simple diagram in which one capacitor is connected to an AC source, and in this capacitor I have considered one space in between the plates of the capacitor which is depicted as S. So here the total charge on the capacitor plates is Q, and the area of cross section of the capacitor plate is A. And here in this capacitor, the direction of the electrical field lines is from the positive charge to the negative charge as indicated by the arrows. Now in the chapter number 2, that is in the chapter of electrostatic potential and capacitance, we have studied that the intensity of the electrical field between the plates of the capacitor is equal to Q divided by epsilon naught A, and by using the Gauss law we can say that the flux which is passing through this surface S, which is lying in between these between the plates of the capacitor, will be equal to Ea cos theta, where theta is the angle between the direction of the electric field and the normal to the surface. So theta in this case will be equal to 0 because the normal to the surface will be parallel to the direction of electrical field. So phi, that is the flux passing through the surface S, will be equal to Ea, and Ea will be equal to Q upon epsilon naught because E is equal to Q upon epsilon naught A. So if I substitute the value of E as Q upon epsilon naught A, I will be getting the flux which is equal to, flux will be equal to Q upon epsilon naught. Now if the charge on the plates of the capacitor is changing with time, then we can say that I, the current, will be equal to dq upon dt, and so what I can do is that I will simply differentiate this equation, that is phi is equal to Q upon epsilon naught with respect to t. If I differentiate it, I will be getting this equation as d phi upon dt is equal to 1 by epsilon naught into dq upon dt. Here epsilon naught is a constant. So this is the equation which I will be getting after differentiating this equation. So from here this dq upon dt is the current, and this current is called the displacement current. So displacement current is equal to epsilon naught into d phi upon dt from this equation. This is id. So id will be equal to phi naught, this epsilon naught into d phi upon dt. Now displacement current is generated in this capacitor due to the changing electrical field, and the conduction current is flowing in this circuit outside the capacitor due to the flow of the this conduction current is due to the flow of the electrons in the electrical circuit, whereas the displacement current is generated due to the changing electrical field inside the capacitor. So I can simply say that the total current in an electrical circuit, in this case I will be equal to IC, where IC is the conduction current and ID is the displacement current. Now this word displacement current has been derived from the fact that the change in the electrical field is also called the electrical displacement. Since this current is generated due to the change in the electrical field or due to the electrical displacement, therefore this current is called the displacement current. So now this I is the total current which is equal to IC plus ID. So inside the capacitor, the total current will be equal to ID, and outside the capacitor the total current will be equal to IC, because outside the capacitor the displacement current will be equal to 0, and inside the capacitor the conduction current will be equal to 0. So from here we can say that the displacement current will be equal to the conduction current. And now another important point is that the electrical field gives rise to the magnetic field as per the Ampere's circuital law, which is given by the line integral of the magnetic field around any closed path is equal to mu naught times the net current which is passing through the area enclosed by the closed path. So Maxwell modified this Ampere's circuital law, which is now called as the Ampere-Maxwell law, and he modified this equation as that the line integral of the this magnetic field around any closed path, this will be equal to mu naught into IC, where IC is the conduction current, plus mu naught into the displacement current, and displacement current is equal to epsilon naught into d phi upon dt. So this will be equal to epsilon naught into d phi upon dt. So this formula is called the Ampere-Maxwell equation. So thank you very much for joining this session. In the next session, we will be discussing about the different types of Maxwell equations. So till then, have a nice day. Bye.